Here at the excelcalcs.com website, users share calculations with each other, and these calculations are all prepared within Microsoft Excel. And it just prevents reinvention of the wheel. You can pick up somebody else's problem because they've already done some work on it. You've got a good chance of knowing that the problem's correct because somebody else has used it. And there's also a whole load of user comments on each particular download. Now today I want to talk to you about Turan Babacan's fantastic new Excel worksheet. He's done some great work on the site already, but this latest offering is absolutely phenomenal. It undertakes a 3D beam finite element analysis all within Excel, but it does it in such an elegant way, it really is worthy of everybody's attention. If I just take you to the file, you can see that Turan's chosen to work in a very graphically orientated way. So here's the model itself. And I think what I'm going to do, I'm going to just talk a little bit about the model, and then I'm going to talk a little bit about how to set the model up. So once you have the model, you can spin it round. It's very easy to do, just by using these buttons down here. The other thing is that we can show our joint labels. The joint labels, or nodes, I would refer to them as nodes, they are points in X, Y, Z space. And between points we have elements or frames or parts of the frame. So element number 7 runs between node 3 and node 6. And we can hold this frame down using restraints. So I'm going to hold this down at the bottom of the tower structure, and they're going to be pin supports there. And at the top of the tower I'm applying some loads, and once we've applied some loads we can see some structural deformation. So that's how the structure is going to deformed. You can also look at things like nodal coordinates, or you can look at the lengths of beam members. Just get that going. There we go. Each element has a length associated with it. I'm going to take those back off again now, just to remove some of the clutter from the website. There we go. And put them back on. Okay. There we go. So it's uncluttered again. Now, let's think about how we could set up our own problems, or how this particular problem has been set up. Turan has set everything out in a very easy to use way, and really I think the reason why I'm so impressed with this spreadsheet is because it has been set out in such an easy way for other users to use. The first thing is we'll define properties, and we'll use each of these links down here. We'll basically work our way down through all these links here to set up our problem. The first one is units. This is set up for SI units, and let's just have a quick look there. If we select SI units, then we're working in metric measurements for each of these dimensional values. If I was to change that to US units, then you can see that they've automatically changed. I'm going to switch it back to SI though. Now let's have a look at the second link down. This is for materials. We can define any number of materials that we care to specify here. And in the third link down we have sections. So this is the section properties that we want to use for this problem. And Turan again has made this very easy to use. The first thing you have to do is select a material, and the material automatically reads from the materials you've already previously defined, and then it allows you to choose a section type 1 to 10, and this is you can see what each of the sections are by using this key down here, and you can see each parameter for the problem. So let's use this one here. It's a simple one. User type 1. So it's this section here. It's got H and B are defined. So B is defined there, H is defined there, and it will calculate automatically the area, the moment of inertia, and the polar moment of inertia for you. So that's how we go about defining sections. Then supports are very easy. 1 means it's free, 0 means it's blocked. So 0 means 0 movement. And if we want to, there's different types here. This particular type means a pin support because it's going to block the displacements in the X, Y, and Z directions, but it's going to leave rotations free. There you go. And a normal beam-to-beam connection here, say between node 8 there, the normal connection at node 8, that's obviously free to move in any direction. So in fact that little symbol there, free, means it's free in X, Y, Z, and rotationally in the X, Y, Z rotational directions too. So we have support types as well. The next thing we're going to look at is nodal points. Nodal points, very easy to understand. X, Y, Z position defined here, and the supports are defined here. So the support at the bottom, where we have a pin connection, is taking, again, reading from the support section. We can select different supports as we like, and the supports between normal beam-to-beam connections are this, like joint number 5 here, which is there, is free to move in any direction, only constrained by its connection to the elements. Then we can go to nodal loads, and you can see here that we've got 40 in the X direction and we've got 25 in the Y direction. That's newtons. The units obviously go through an update, so they're easy to understand exactly what we're doing there. And now let's go define some bars or elements, but there's a bar number here, or element number if you like. It tells you what the distance is. It tells you that it's running between two nodes, 1 and 4. So let's take this example here. Bar number 1, or element number 1, runs between node 1 and node 4. There you go. And the section that is being used is section 1, so it's reading from that previously defined section, which is there. Now, you could also introduce point loads or moment loads or distributed loads along the element as well. Now, I haven't done that for this particular problem just to keep things simple, but you could do that. But then the problem is then fully defined. We have forces, we have nodes, we have elements, we have restraints, and we've calculated a deflection, and we can now go and look at the calculation results. So we can look at the element forces. So if we look at element 1, there's 2 nodes, and each node there's 6 forces, 3 x, y, z, fx, fy, fz, and 3 moments, mx, my, and mz. And you've got the same at the top. So there's 12 parameters for every single element here. So here we go. These are the forces in newtons, moments in newton millimeters for the first node, and then for the second we have forces and moments again. So the great thing about this is that everything's in Excel. So if I want to do any kind of member assessment using some of the Eurocodes or using AISC or any of those things, I can directly get at the values in Excel. I can do additional calculations to check that the sections lie within their code parameters or past their code requirements. Turan has even set out a flowchart because he likes to show exactly how he's worked, so we're not trying to bamboozle anybody here. This is setting up exactly. If you want to, you can go look in detail at how where all the different calculations are done and how all the graphics routines are set up. It's all very transparent, and he's even produced a list of features that he's hoping to introduce later in the year to make the worksheet even better. Now, I think this really, I really am taking my hat off to Turan here, and I'm taking my hat off to him not only because it's a phenomenal calculation, but I think it's the way it's been put together using features within Excel. It's as sweet as a nut, really. Absolutely perfect. So thanks again, Turan, and I hope everybody enjoys using your superb work. Okay, thank you.